first, but then.
Okay, so quick review from yesterday is the idea of work. There will be some problems, at least two, at least one or two on the next quiz. Of course, we got area between curves, we got volumes, all these different types of volumes. Probably volumes will make up the majority of the quiz, or at least a good part of the quiz, because we did spend a lot of time on volumes. There will be one or two work questions, and they will either be a spring or a rope bucket kind of problem. And then the new thing we have to learn today, there will be some of that as well. So the whole thing with work is that we need to have some sort of force equation, which is pounds, is what we're going to be measuring that in. And then the dx is the feet, and so we get foot pounds or inch pounds or whatever the distance unit is here. Now, for a spring, this is how you get your force. That's the force equation that goes inside of the integral. For a rope and bucket, it's adding up the pounds that you're lifting. The bucket, the water, the rope. Okay, or like the elevator problem, be the elevator maybe plus the people in the elevator plus the cable. But same problem, same exact scenario. Okay, with the bucket, of course, as you lift up, you have less and less rope to lift, or less and less cable for the motor to lift, so that's a changing amount. With the bucket, you could have water leaking out, so that could be a changing quantity. With the elevator, I don't know, people could be leaping off or something as it's going up, maybe. I don't know. I don't know. How else would that change? I don't know. So, yeah, they're jumping off of each floor. In a linear fashion, three people per floor. There'd be some rate, right? We do. All right. Probably not that kind of situation. But, all right. So, number 12. There was a question about number 12. What was number 12? What was that problem? The water leaking?
Half of the water was gone by the time it reached the top.
Okay, so we're looking for an integral. So the bucket weighed how much?
80 pounds.
Now, is that with the water?
Yes.
So that's the bucket and the water together. So we don't have to separate. Okay, so one of the ways we said yesterday is we could make kind of this would be your y, x, this would be feet. I assume it was feet, right?
Yep.
That's 41.
And it's 75 feet deep. So when we've lifted 0, right, when we haven't lifted at all, how many pounds
80.
do we have? Is it 80? When we get to the end, when we've lifted all 75 feet, how much does it weigh? 40. So this would be one way to do this. Now, the other way we said is if you think of where we're lifting, which this is 75. If we've lifted it to here, that's our x. So this would be 75 minus x, right? And so we could think, no, it's 75 feet. I think it's feet. Okay? Well, it wouldn't work bad at all because to do it that way, we needed to know how many pounds per foot of water, right? What were the pounds per foot that the water was at any given time, right? Well, how many pounds per foot do we have? We're losing 40 in 75 feet, right? So whatever 40/75 is, that would be pounds per foot of water, right? So at 0 feet, well, wait a minute. Let me think about that. So that would be, so at 0 feet, and then if we do 75 minus x, okay? So this would be, when x is a 0, oh, you're right, that would just be 40. So we want 80 when x is 75. Yeah, so then we would, yeah, I'm sorry. I was right. I was right the first time. But we'd have to make an adjustment to this. So we're losing 40/75, right, pounds per foot. But then what I would do is I would test this. So I'd say, okay, at 75, or let's put a 0 in here. When I put a 0 into here, the 75s is canceled, we'd have 40. Wait, we don't have 40 pounds though. We have how much at 0? We have 80. So I would add 40 onto that, okay? And then when we get to the end at 75, what happens? 75 minus 75 is 0, which wipes that out, which is just 40. So that would work, right? So you'd have to make a little bit of an adjustment there for that. So this would give you how many pounds of water you have, and water and bucket at any length of rope, okay? So when X is 0, we the 75 is cancel, we'd have 40 plus 40, we have 80 pounds of water and bucket. And when X is 75, this would be 0, we'd have 40, and then we'd have all the increments in between. Okay, so that would work. That'd be one way to do it. Yes.
I did 80 multiplied by 150 minus X divided by 150.
80 times 150 minus X. Say that again.
Over 150.
Over 150. Okay. That's going to be very similar, right? Because if you look at this, what is that going to be? So if we simplify mine and simplify, but let's test yours. Let's put a 0 into here. You put a 0 in there, 150, 150. We cancel, you have 80. Put a 75 in here, 150 minus 75. You'd have 75 divided by 150. That'd be a 2 on the bottom. 80 divided by 2 is 40. So it works. That's just a different version of this. Okay, so it works, and that'd be fine. And I'm fine with any of these ways of doing it. Now, the other thing I told you yesterday is if you've made this table, now just do a slope, right? Just do a slope. So 80 minus 40 on top, you always want your y's on top, and then 0 minus 75. So that's 40 over negative 75. That would be your slope, right? And so now you write an equation of a line, so you do your slope. Pick one of these points. Probably that one is the best one to pick, x minus 0 plus 80. And you end up with that equation right there. And that is also just another version of these two equations right here. Okay? Either way, in this one, we put a 0 in for x. This is going to wipe that out. We're going to get 80. Put a 75 in for x. The 75 is cancel. We have negative 40 plus 80, which is 40. So we get those 2 points. But they're all dealing with kind of the same thing. Notice in Jamie's 80 divided by 75 would be the same as 40, or excuse me, 80 over 150 is the same as 40 over 75. Okay, so
That deals with the weight of the rope.
we haven't done the rope. This is just the water.
Oh, okay.
This is just the water in the bucket because it's leaking. So that's changing, just like the rope is changing. So it's a very similar way. So when you write this out, it's a very similar way of doing it with the rope. Okay, this is just a little more concrete, a little more, you can just put down, okay, I start with this, I end with this. As it's changing, now I can just do it as a point slope kind of thing. This is, kind of thinking it through a little bit as a rate kind of thing, but it comes out the same. So any one of those would be okay to go in here. Okay, so we'll put Jamie's in there just because it's maybe a little faster to type in our calculator or whatever, but it doesn't really matter. You could simplify and all that. So that's pounds. Okay, because remember that was like a y equals x was the feet, and so that's giving us pounds. So at any given x value on its way up, any given x value on its way up, we could plug that in here, and we'd have how many pounds of water and bucket we have. Now we need the rope. What's it say about the rope? Per foot, it's 0.65 pounds per foot. Okay, so the simplest way is to just take 0.65 times 75 minus x. That's probably the simplest one to do on that one. Okay, or again, we could say we can make ourselves an xy when there's 0. The difference is when they give you pounds per foot, we need to know what would we put here. When we haven't pulled up any rope, when we have all 75 feet of rope, how many pounds would go here? You'd have to take 75 times 0.65, right? If it's 0.65 pounds per foot, then when we have all 75 feet of rope out, we need to know how many pounds that is. Well, what is 75 times 0.65? Somebody got it? I'm just waiting. 48.75. And when we get down to 75, when we've lifted all 75 feet of rope, what's the rope weigh? 0. Okay, so you would have to make, when they give it to you as, you know, it can be given either way. And the problem we had that we started with yesterday, they said the rope weighed 1.6 pounds, right? They just said the rope was 1.6 pounds. And then there was 20 feet of it, so we had to take 1.6 divided by 20 to get the pounds per foot when we did it this way. If you're going to do it this way, you need the total pounds of rope with 0 feet pulled up and with 75 feet pulled up. So you need the total pounds. So that's why we had to do that. So now what I do my slope. So 48.75 minus 0, 0 minus 75, negative 48.75 over 75, which is that number right there, negative. And then we would put that, so it'd be negative 0.65, and then we would pick this point right here, so we have x minus 0 plus 48.75, just doing our tangent line, or just our line equation, right, point slope form. So there's our slope, there's our point, put that there, or that one, same thing. It's the same thing, okay? And then it would go from what to what? 0 to 75, okay? And we plug that in, and we should get 6,328.125 foot-pounds. Is that what you had?
Yeah, but I did them together. I did the rope
Oh.
and the water together.
Yeah.
Not allowed.
Sure. Here's what she's saying. She's saying, okay, when she just made a table that was this. Here's X, here's pounds. When there's 0 feet of rope pulled up, what do we got? We got 48.75, so you went ahead and multiplied that. The 0.65 times it. So we got 48.75 pounds of rope plus 80 pounds. And you got that same answer? Okay, they're both linear. Okay, not the same, right? They're not changing at the same rate, but when you put them together, there'll be a combined rate that those two are changing. So we start, so we have 80 plus 48.75, so that'd be 128.75. So there's that many pounds. And once we get all the rope pulled up, what's it weigh? 40, right? Because we have no rope and we have 40 pounds of water in bucket. Okay, and so now we can just do a slope on that. So we can subtract those, which looks like it'd be 88.75 over negative 75. That'd be my slope. And then x minus 0 plus 120. Was that the numbers? Those look familiar. Is that what you have? Okay, and then that'd be that integral from 0 to 75. And you got that same number. Okay, 6,328.125. And you should. That's a good idea. That's a good idea. You got two changing quantities in there. Go with that. So, again, what do we need to have? We need to have pounds in here. What are the pounds that we have? And it's a changing amount. Somehow it's going to be changing, right? It's changing in the rope bucket problem. It's changing because we have less rope as it comes up. And also, if it's leaking, we might have less water. But if it's not leaking, then it's only the rope we have to worry about, and the rest of it just adds on and stays constant. And then, of course, in the spring problem, the force changes, and that's why we have that equation. Okay? So, just to review very quickly on a rope or a spring problem, so let me just throw this out here. So let's say you had 5 pounds of force were needed to move it from 6 inches to 8 inches. Natural length was 6 to 8 inches. What would I do first with that information? 5 equals F is KX, right? So 5 equals 2K, right? The 2 is X, right? 2, so 2 inches, we move it 2 inches, so K would be 5 over 2 or 2.5. So in my integral, I would put my integral, I would put, right? My integral, I put my force equation, right? K times X, so 2.5X. And from, now we're going to move it from 8 to 10. Well, this is 0, right? Natural length, so that'd be 2. That'd be 2 to 4. There's really, I mean, it's that easy. There really is there's nothing else that a rope problem can really happen. It could be worded differently. You might not, I mean, but they got to tell you that for a certain amount of pounds of force, it took to go so far, okay, it took so much force to go a certain distance, you get that. That gives you a force equation, and then you got to figure out what lengths you are to go into there, and that's all she wrote. Okay, there you go. There are those problems. Okay, let's get to your notes here. Let's talk about section 7.4, which is back to differential equations, our last go around with those. Okay, so as you're getting ready to write down here, differential equation is what? Differential equation is what? I would almost think you were reading that right out of the dictionary. That was perfect. An equation involving derivatives. What is the solution to a differential equation? It might involve an antiderivative, but it's the original equation y or p or whatever variable you're using. So if the differential equation has derivatives in it like y primes or p primes or h primes, then we're finding the original equation y or p or h. Right? That's the solution to a differential equation. And oftentimes we get an initial condition along with the differential equation. That's called an initial value problem, an IVP. Okay? And we can find it. Now sometimes we can do an antiderivative to get the original function, but that's only when we have just x's or t's in it. And those were the only ones we really knew how to solve. So up until today, any others, we just memorized a couple of them, like this one, right? This is one of those we just memorized the solution. We're trying to find what y equals here, okay? But as of today, we're now going to learn out how we actually can solve this, okay? And it is going to involve an antiderivative, but not a straight antiderivative. I can't do an antiderivative here because this is really with respect to x or t or some other variable. So I can't like raise that up to 2 and divide by 2. That doesn't work. What is the solution to this since we had memorized this already? What is the solution to this one? AE to the KT to the 3T, right? That's K right there. Right? So yeah, it's KT in general. If this was y prime equals KY, then, so this solution should be that right there, right? And at this point, we were just memorizing that. And those of you that got that right on our last quiz where we had to, that was one of the options where I said, write down the solution to this. Some of you did that, and you remembered that was the solution. Now we're going to learn how to actually solve it. Now, these are called separable differential equations. If they can be solved with this technique, they're called separable differential equations. Now, not all differential equations are separable. It's kind of like in algebra class. You learn about different types of equations. You got linear equations. You spend all of algebra 1 in pre-algebra even dealing with linear equations, right? 3x plus 7 equals 10, solving for x, right? And then later in algebra 1, you get into quadratic equations. What do quadratic equations have in it? What's a quadratic equation? Oh my God, you've seen it. You guys are really sharp. Oh. What's a quadratic equation? It's got what in it? What's it look like? The graph is approached x squared. Thank you. Yeah, it's got x squared in it. Quadratic equation got x squared in it. And then you learn, and then you spend a lot of time solving those. You factor. You use a quadratic formula. You complete the square, right? You can graph them. They make parabolas, right? Then you might, I don't know, you might have went into cubic equations, and they have what in them? There we go. Now we're coming back. X cubed. They have x cubed in them. Right? What those look like. And then you get into some exponential equations and log equations, and some of that's in Algebra 2, and then maybe in advanced math we learn different ways, and there are different strategies, right? There's different strategies for solving an exponential equation or a log equation, right? And a cubic, so you learn these different strategies for these different types of equations. Well, same thing in differential equations, right? When you get done with calculus sequence, if you're going into engineering or something where you need multiple levels of math, one of the next classes you will take after that is differential equations, a class in differential equations. And what that's about, much like Algebra 1 and Algebra 2, and even into advanced math, you learn about different types. You learn how to identify different types of differential equations, and then each one of those different types has a different way of solving it, a way to solve that differential equation, which means a way to find the original function. Okay? So, in your book, everybody get your book out. Before we talk about solving this, I want you to just quickly be able to identify what is a separable differential equation versus one that is not. Okay, be kind of like asking you to identify the linear equations from a group or the quadratic equations from a group. So you got to know what they kind of look like. So if you turn to page 4, .441. Okay, 441. All right. Separable differential equations are typically going to involve multiplication and division. Now, the reason we're going to call these separable is we can separate the x and the y, or the t and the y, or whatever it is. Now, in your notes, the first step you're going to make in a problem like this is instead of writing y prime, you're going to write dy over dx. It's got to be written with this Leibniz notation. Okay, now we don't know that it's x in this problem if that's all we're given. So I'll just use x. It could be a t, or it could be, t or x. Those are the ones we usually use. But I'm going to write it like this. Now, what we mean by separating is we want to get the x's all on one side and the y's on another. Now, since the dy is on top, that's going to stay here. Since the dx is on the bottom, we're going to multiply it over to this side. We're going to separate the x's and the y's. So I'm going to move this dx over to this side. Now, that gives me dy equals 3y dx. Now, I don't like that the y is over there with that x. The 3 I don't care about. The 3 can stay here, or it can divide over to here. Probably leave it there, since I'd rather work with a 3 than a 1/3. But it doesn't really matter, okay? But I do need to get that y over here, so I'm going to divide by y. Now, for reasons that you'll see, I would rather write that as a 1 over y when I divide it over there, and not a dy over y, because an integral is going to get involved here. And when we wrote our integrals, we always said it was better to have fractions and make it look like this than to write it dy over y. So when I say I'm going to divide by y, I'm going to write it like that. And on this side, I'll have my 3 and my dx. So now I've separated them. I got the y's on one side, I got the x's on the other. The 3 I don't care about. It could be on either side, doesn't matter. But it's a lot easier to have it over here as a 3 than it is to have it over here. So usually I leave the constants on this side. Usually. Okay? And not have them over here. But it doesn't really matter. So that is separating the variables. Now, if you can do that with legal algebra, then it's a separable differential equation. So if we look at page 441, you notice the first one they have there, ty. That's separable. I can divide the y over, I can bring the dt over to the right, and I've got it separated. The next one, again, I can multiply the y over to the left and get the y's over there, and I can leave the sign t on the right, and I got the t's and the y's separated. Look at the next one, same thing. I can separate those. Now, if you go down to the middle of the page, you've got a couple that are not separable. For example, you've got t plus y in the middle. You see that one? You cannot separate that. I mean, addition and subtraction, we are not going to be able to separate. So if t's and y's are added or subtracted somehow, you're not going to be able to separate them because it's got to involve multiplication and division. If I multiply the dt over to the right-hand side, even if I distribute it, I would have a dt stuck to a y with some more plus. There's no way I could divide it out. I could try rearranging all I want. I'm not going to be able to separate those. Okay? Same thing with the one that's got sine of t plus y. So there's going to have to be some other technique involved to do that one. Okay, and you'll learn about that in a class on differential equations. We're going to deal with ones that are separable. Now, when I say you can't have addition or subtraction, that means you can't have an x and a y being added or subtracted. But if I had this, right? right? Now this actually is an easy one because it just has x's in it. But if I had this, or if I had, then I could multiply the dx over here and I'd be fine. Or if this was 1 minus y, I'd be okay. Because I could multiply the dx over here and do what with the 1 minus y? I could still divide it over, and I'd have this. So I could treat the 1 minus y as one thing, and I could still divide it over as a single quantity, and that would be fine. But if this was x minus y, then that doesn't work, because I divide it over, now I got an x over here, and there's just no way to get those separated. Okay? So it's possible to have an addition or a subtraction in there, or if this would have had an x on it, let's say this had an x outside of here, right? That's fine. I could divide the 1 minus y over to here, and then the x would still be setting over here, and then everything would be fine. I got the y's on one side, I got the x on the other. Okay? So that's how, now I'm not going to give you any on the quiz where it's not separable, right? If I give you one, then you can do it. All right. Now, on the AP test, sometimes they'll use this terminology. They'll say, by separating variables, solve this difference equation. Or use separation of variables to solve this difference equation. But a lot of times they don't. They just say, solve this difference equation. That's really the only solving method you have to know for the AP test. Now, the other one would be just doing a straight antiderivative, which if you just have x's over here, you can do, right? I mean, you can just do a straight antiderivative. These are all x's. Okay. But otherwise, this separation of variables is the only other technique we have. Okay, how does it work? Well, once we get to here, we just do the integral of both sides. I mean, look at it. It's begging to have an integral on it, right? It's got a dy, it's got a dx. I mean, it just seems like it needs an integral on it. We do the integral of both sides, okay? Which essentially means do the antiderivative, right? The indefinite integral. So what's the antiderivative of 1 over y dy? ln of y. Now, technically, we should have absolute value around that, so I'm going to put it there. Now, what about the plus c? Shouldn't there be a plus c? Right? When you do an antiderivative like this, there should be a plus c. Right? Equals, now what's the antiderivative of 3? dx. That'd be 3x plus c. Now, what am I trying to find? I'm trying to solve this differential equation. So what am I trying to find? What y equals, right? I'm trying to get what y equals. So now I can take and solve for y. Now, some people say, well, what happened to the dy? Well, what do you mean what happened? It just said take the antiderivative with respect to y. So we did it, okay? Now, I want to get the y by itself. So you might say, well, I'm going to subtract the c's. Well, what happens if you subtract the c's? Careful now. No. Because they're not necessarily the same constant.
And why do we have the same variable?
So why don't we call it C1 and C2? Now, it's not the same, right? C, remember, is some arbitrary constant. So if I want to get y by itself, I'll subtract C. Well, what's C2 minus C1? C3 or C whatever. It's just C, right? So here's what I'm going to do from now on. Because that'll happen every time. Every time you do this, you're going to get a plus C here, you're going to subtract that C over. So when I do these from now on, I'm not even going to do the C on the side with the y. I'm not even going to do that one. I'll just do the C on the side with the x. Because I know I'm going to try to get the y by itself. And so I know there's a plus C, and then it'll subtract over there to make another C. And I'll just put it over there. That'll just save me a step. Okay, now how do we solve this for y? E raised to the that equals that, right? So y equals e raised to the 3x plus c. Now, we don't have to worry about y being positive here. We don't have to worry about that part of it because when we solve that, that's going to be, so we don't really have to worry about the antiderivative piece of that. Okay? Now, you look at that and you say, wait a minute, I thought it was going to end up being this. It's close, but it's not quite. Well, there's an algebra thing. When do you add powers? When you multiply two things with the same base, right? So wouldn't it be true that this would be e to the 3x times e to the c? Wouldn't that be the same thing? Because you're multiplying the same base, you'd add the powers. So that'd be e to the 3x plus c, right? And e is just a number, right? and c is just some arbitrary number, some constant. So what's e raised to the c? Just some other constant, which we could call c again, or we happen to call it a this time. So, and then I'll throw that around in front. And that's how that is the solution to that differential equation. Y, and we could have done it as y prime equals ky, and then all these 3's would have just been k's, and there you go. And now you can see why we get that. Okay, so oftentimes when you're dealing with these exponentials, you get a sum inside here. What we do is we just split it apart like that, and we throw that constant out in front. Okay? There you go. That's solving by separation of variables. All right? Let's do another example. Here's another one that we have done where we memorized. We had Newton's law of cooling. Now, this actually is Newton's law of cooling. You may not recognize that, but this was Newton's law of cooling right here. Right? Doesn't that look like this? The 1/25th is the K. The 300 is the big T. That was like the room temperature. Do you remember what the solution was to this? It was very closely related to this one.
Nope. No one remembers it.
Wow. Okay, Jamie. Thanks for speaking for everyone. All right.
No one else is
Appreciate that. Well, you didn't give much time, but that's okay. I'll trust you. All right. So it was this right here. Big T plus AE to the KT. Right? Big T plus AE to the KT was the solution to that. Okay? All right. Well, let's see if it actually is. Let's take a look and let's solve this and see what happens. So I want to separate these. So I've written it actually instead of W prime, I wrote it like this. Okay, so what do we want to divide? What do we want to move? What do we want to do?
divide the W minus 300 over.
I would agree. I would just leave that here. I know it's a fraction, but I think I would still just leave it on this side because we're going to want to get y by itself anyway, or in this case, w. So why move something over to the w side if you're just going to have to move it back anyway, right? I mean, we have to move the w's over there, but the constants we might as well leave over here. So this is going to divide over to here. I would rather write it as this, right? And the dt is going to go over to the other side. The 1/25th will still be there. It's going to look like that, right? Now we're going to throw our integral symbol on both of those. And what is the antiderivative of this? ln of that, because all that is a shift, right? That's just a shift 300 of a 1 over w. So it is just ln. If you don't believe it, you can. I'm going to put bars around that, but it doesn't really matter. Again, what would be the derivative of ln? It'd be 1 over what's on the inside times the derivative of the inside. Well, the derivative of the inside just be 1, right? With respect to w. Now we're talking about with respect to w here. So the antiderivative inside just be 1. So that would be that one. And then what's the antiderivative of 1/25th? 1/25th, not x.
Sorry,
T plus c, right? With respect to t this time. So it's 1/25th t and then plus c. Okay, and so how do we solve this for w? E raised to that equals that. So w minus 300 would equal e raised to the 1/25th t plus c. And what can we do on that right side? Split that apart. So this would be like w minus 300 equals a e to the 1/25th t, right? And you separate those just like we did on the other page. So this would be e times e to the c. Okay, and then add the 300 over, and we get 300 plus ae to the 1/25th t, which sure looks a lot like this one up here. Big T, which was our 300, plus ae to the kt. K was the 1/25th. Okay, so those were those two that we just talked about and tried to memorize. Well, now by doing this separation of variables, of course, you can see why we couldn't do them back then because we had to talk about integrals and all that stuff with dw, dt, that kind of thing. But we can actually separate the dw, the dt, so Leibniz notation works really well here. and we can solve and find that original function. Okay, let's do one more. Okay, let's look at this one. So you don't think that every one of these is going to have natural log in it. It's not. Okay, you guys try this one. Go ahead and separate it. Do your antiderivative. Try to get the y by itself. Oh, by the way, I forgot on this last one, then if you're given an initial condition, right, you would plug that in. So we'd put a 1400 in here, 300 plus a e to the 125th times 0. E to the 0 is 1, so a would be 1100. So now the equation, the answer is 300 plus 1100 e to the 125th t. So when you're given an initial condition, you then plug that in and you find that missing constant. Because every time you do an antiderivative, you're going to get a c. Now it turned into an a here because of the e that we had in there. C turned into an a because of the e. All right. So anyway, next one. So go ahead and finish that.
Yeah, Mr. Clark.
What?
You definitely use the natural log, right?
No, you definitely do not. Okay. I was just going to mention that. Why did you ask? I was just going to say, okay, so some of you have a little bit bad habit of thinking that anything that is 1 over is going to be ln of that thing, right? Now, is that correct? No. Now, in the first two we did, we had 1 over y, and we had 1 over w minus 300. It was the first power. If you have an antiderivative of 1 over x cubed, how do you want to write that? You want to write that x to the negative 3 into a power rule, right? That's what you want to do, okay? So, again, this is why we took the gateway test, and this is why we have to review this stuff, right? Is because all these antiderivative rules we need. So I've done this part, okay, so everybody got to hear, I'm guessing, right? And so at that point, because, and this is why we're doing this one, and at this point you're thinking the last two and you're thinking that's natural log. No, it's not. You're going to actually do what on this left side here? You're going to write that e to the negative 1, right? Because we don't do natural log with every single thing that's 1 over something, right? And we don't do a power rule on this one, right? I mean, I gave you an example of a power rule. But E has its own set of rules for antiderivative. Okay, so go ahead and go from there. step after what I had given you there, the antiderivative of e to the negative y, I have to kick out a negative, right? It's its own antiderivative. E to the something is its own antiderivative. If this was e to the 2y, what would it be? Antiderivative. This is e to the 2y, what would it be? 1/2 e to the 2y, right? You have to kick out, right? It's a reciprocal thing. When you have a constant, you're doing an antiderivative, right? Because when you do the derivative, you kick out a 2, and the 2 has to cancel 1/2. Okay, so there'd be a negative, a reciprocal -1, but that's still -1. Okay, and then over here, that'd be x cubed minus 3x squared, and then plus a c. Okay, what is your next step now? Multiply by -1 or divide by -1, right? Trying to get the y by itself. So we divide by -1, negative, positive. Now, what happens when you get minus c? Same as plus c. I usually just keep it plus c. Okay? So you're going to multiply by -1, but I would keep that as a plus c. Okay? All right. Then, so you're going to have that over there. So you're going to have e to the negative y equals negative x cubed plus 3x squared plus c. Then what? Natural log of both sides is a good, or you can just convert it to a natural log. But when you do the natural log of this side, what do you get? Negative y, right? And then natural log of that side. Now, it might be good to put bars around that because we do want that to be positive. This needs to be positive, but it will be. It's good. This e to something's always positive, so we know that's got to be positive right there. Okay? So we're actually okay with that. So you do the ln of both sides. So you got that. Okay, and then what? Divide by -1 or just multiply by -1, either way. So you get y equals negative natural log of the quantity negative x cubed plus 3x squared plus c. Okay, and then don't forget, what's the next step? We forgot it on the last problem. Plug in our initial condition, right? So for x, we put a 1, that'd be -1 plus 3, that'd be 2. 2 plus c would be on the inside, and we put a 0 in for y. So we'd have 0 equals ln of 2 plus c. 0 equals ln of 2 plus, oh, negative, there's a negative, forgot about that. Negative ln of 2 plus c. But you can divide by negative, and it's still positive, and so what do you do with that right there? How would you solve this? E raised to the, right, yeah, same thing we just did on the last two. Right? E raised to the 0 equals 2 plus c. E raised to the 0 is 1, would equal 2 plus c, right? E raised to the 0, which is 1. And the negative's out of there. I've divided the negative out of there, and that's still 0. E to the 0, which is 1, is equal to 2 plus c. And so c is -1. So right here, you just put a -1 in place of the plus c, and you've got your final answer. Okay? So, be responsible on the quiz next week for a couple of those kind of situations. All right, so let's start working on some here. On page, this is 7.4, so I think that's 440 something, 450, I don't know, somewhere in there. There are a number of these problems we have to separate. Now, I think some of them, let me look here real quick. I think some of them have, yeah, 17 through 22, they have a initial condition. So it says find the solution of the IVP. So that's what we were doing. Initial value problem has an initial condition. So those you had to do that. And then on 27 and 30, they do not have an initial condition. Okay, so on 27 and 30, you'll have a plus C in your answer. Now, again, the idea here is that you'll be able to do these antiderivatives without your calculator. Okay, I mean, that's where you're going to have to do. Now, yes, on the quiz next Wednesday, when we do these, you'll have your calculator. But on the finals, and we're going to go back through some old AP tests that have almost every year on the AP test, and in our final for sure, you're gonna have to do this, and it's usually in the no calculator part. Okay, so what do we got? About 15 minutes.